okay, and it just told me something like, don't ever get the other one.
All right.
That doesn't strike a weird chord.
So, let's see. Today we're going to talk about OpenMP mostly. We need to wrap up this thing. We were talking about various optimizations last time, I think. We didn't finish up the part about functions, so we'll do that. And then start looking at OpenMP. OpenMP won't be on the midterm, so I guess today and Thursday, well, today we'll talk about OpenMP. Thursday we'll try to do a little review before the midterm, which is next Tuesday. Homework was due now, wasn't it?
Yep.
Yeah. Who finished it? Okay, pretty good. All right, so maybe I'll just briefly mention some things, parts of my solution. So, excuse me, for the 3-second like finishing on time sort of business, it's more of a user experience affair. It's really weird when a program finishes much longer. When you say it should run 3 seconds and then it takes 3 minutes, that's really weird. So we should fix that. It's not necessarily that you can run a correct experiment if you have so little time, if it actually takes 3 minutes to finish it, right? So my solution is to just use alarm. So set up an alarm signal and then shut down the program, print a little error message like this. We didn't have time to initialize, right? That was the problem. I don't know if everyone noticed, but probably, given the discussion on Piazza. Initialization took very long. With the rest of the program being buggy, initialization just took a really long time, and the timer was only around the parallel part. Well, actually, not really parallel in this case, but only around the part where we're doing inserts and updates once we have a well-grown tree. Okay, so fix there, just put a signal on it, pretty simple. How long, or an alarm, that creates a signal, a sig alarm, so you'd have to catch that signal. Okay, so how big should the tree be? Well, so we're inserting 100,000 elements. We'll have some overlapping keys. So maybe it'll be a little smaller than that. And then we're inserting and updating for a while, and every time we insert, if the tree is size 100,000, every time we insert, it's a 50-50 chance of missing, and or sort of adding a new element. And if we're deleting something, it's a 50-50 chance of there actually being something there. So we're going to kind of end up at 100,000 in the end, right? Maybe it'll kind of grow up to 100,000 for a little while, but it'll sort of meet some sort of like equilibrium there. So what depth tree are we talking about? That's really what's important for the performance of this thing, because it's a tree, so we have to traverse all of the levels of the tree, right? 100,000, so 16 is 65,000, right? 2 to the power of 16 is 65,536. So it'll be, 16, 17, 18, something like that. But then if you say profile the program, you'll see we're spending really a lot of time traversing down these left edges and not a whole lot of right edges. So the tree was desperately unbalanced, and you probably found a depth of, I don't know, thousands probably. Probably not 100,000, but thousands. And the reason for that was a bug. So in the struct, let's see, the element of a tree, it has a value and a key and a value, right? And so we're inserting keys that are between 0 and 200,000, but the size of the key itself is a character, right? So that can only fit 256. So now we're losing many of those bits, and we end up only getting values that are on the left side of the tree. So we're getting really unbalanced values. Okay, at least that was the my diagnosis of it. So if you just fix that, just make it a long or just an int even, then you would get a nice balanced tree. Okay, and then there was the final bit. It was still running kind of slow, right? Slower than you would expect. And this one's harder to find. So now we have a well-balanced tree, but it should be going a lot faster than it did. And the reason, some of you I think sent me private messages about this, is the value in the element. There's a value. It's a pretty large value field. And okay, so in our test case, we weren't really using that, but we have to preserve the functionality of having room for that large value. But the problem that you run into, did anyone catch what actually happened, like with this large value? What's the problem?
Size of the total struct was 4,072 bytes, which was just short of a page.
Oh, you got 4,072. Interesting. Yeah. I wonder
I
why.
think it depends on the size of your key.
Yeah. Okay, I'll have to fix that for my next iteration of this homework.
4,080.
Yeah. All right. It was meant to be 4,096 exactly, in which case you get a really bad situation, but it was still bad if it's 4,080 or so. So basically, what you end up doing is not using your cache efficiently because of this cache associativity problem. Right, many of our keys end up on in the same bucket in our cache. And so one nice solution for this was to remove that sort of statically allocated array and just put a pointer in there instead. And then whenever you make a new element, you just malloc space for the value, and then free the value when you delete an element. So then, we're spending a little bit more time on malloc because that's simply slower. There's an extra malloc. But on the other hand, we're getting better cache utilization. So in the end, it was a better trade-off. Yeah.
If I do a malloc of the buffer size right after creating the node, that portion of memory wouldn't be mapped like exactly after the node. So there's still will be this problem.
Well, no, there's no guarantee, but generally speaking, malloc will keep separate lists for different sizes of elements, and it'll take the first. So let's say if you're passing in different size strings, then certainly they would be all over the place. But you could end up perhaps unlucky and have them all together. That would be more unlucky than this case, I guess. Yeah.
Oh, I sort of just copied the pointer to the string that was passed into the function.
Ah, okay, yeah, that's a bug. It'll run faster.
Yeah.
But unfortunately, that string is disappearing. I mean, at least in a normal case. For this test case, yeah.
Depending on how the user allocated it now.
Yeah. If the user has a memory leak, you're okay. Feature, yeah. I mean, it wasn't really part of the test case here. We'll see what Ben, who is fine, by the way, has returned to service. We'll see how he decides to grade this sort of thing. There'll probably be a little deduction, but yeah. Yep.
So I ended up using that macro that you had defined in the bench list.h, which forced it to be cache aligned. Yeah. And I ended up getting the right result for it, but it doesn't seem like that was what you were intending.
Interesting. Okay, so you put you made your value struct cache aligned. You're saying.
Yeah.
I don't know what that means for a malloc struct, actually.
So you had I actually changed the size that was being malloced. So that macro that you had, it redefined the size so that it was actually cache aligned, and then I malloced on that size. At first I actually had a seg fault with it, and then the bug that someone had addressed with the greater than, that ended up fixing it.
Okay.
Sorry, probably too much detail, but.
So it could be that well, probably what happened. I don't know exactly how you got this cache alignment, or even what it did, but maybe it just made the size of the struct an even cache
Yeah.
line or something. And it could be that you kind of ended up a little lucky in that struct was large enough now that you don't get so much of this cache collisions. Yeah, these things are a little hard to predict, especially when people come up with all sorts of different solutions. Generally speaking, this cache alignment, the memory address alignment that you can specify, right, with a __ attribute aligned. What does that mean? For a global variable, it's pretty easy. It's just the address of this thing will be aligned as specified, right? So with a 64-byte alignment, the first 6 bits, the lowest order 6 bits of the address will be zeros. That's it. But if you're defining a struct, that's just a type. It's not a specific variable. So okay, maybe it's okay if you say any variable of this type has to be aligned this way. So when you say global, if you allocate a global variable, say we say like this: struct, my struct, blah blah. Close enough. And then I say struct my struct s, like that. Right. So in this case, I think the compiler is smart enough that it realizes that s here is what should be aligned. Right. The address of s needs to be aligned. But generally speaking, the type itself can't be aligned, because you could imagine taking any pointer and casting it to a struct, my struct. Right? And that pointer is what it is. You don't go and change that. And when you malloc something, malloc doesn't accept that sort of parameter. Malloc is a function. It's not a compiler construct. So if you say, oh, I want to malloc 56 bytes, you get 56 bytes. It doesn't say anything about alignment. And so whatever you cast that malloc value to, there's no guarantee that that's going to be aligned as you said. So probably there's something else going on there.
I can show you after class.
Yeah, that'd be interesting. Okay, so yeah, so basically anything, you could do a lot of different things there to make sure you don't get that weird overlap of addresses with respect to cache lines. You could make it bigger even, like make the value bigger, make it 5 kilobytes instead of 4, and probably be okay as well.
Yeah.
But probably it's a better idea to not use so much memory and just use malloc. At least that's what I decided to do. All right, so the next homework is going to be parallelizing this tree one way or another, maybe 2 ways. And to do that, we probably need to, well, we could do it with pthreads. Maybe we'll do both. Right. We can do it with pthreads, or we can do it with OpenMP. I think OpenMP is, in a way, really ugly, and in a way, really convenient. I'm a little torn, so we'll spend some time. Okay, but I promised we would do that, the rest of the compiler stuff first. So let's see. I think we ended somewhere here. Does this sound familiar? Look familiar? No, probably not. Well, close enough. So we had a loop like this. I don't know, but maybe we were just saying ink. And we noticed that the compiler decides to just replace this function call to ink with just a code for ink. Right, so that's inlining the function. And then once that's in there, now we see, oh, it's a constant number here. And so it's actually replacing the whole loop with just add, what, 1 billion to I. And that was that, right? So there was a sort of one thing that the compiler can do, or the optimizer can do. But it can only do this when it actually knows what's inside of inc. Right? So when if your inc function looks like that, and it's not defined within the visibility of the optimizer here. The optimizer doesn't know which object we're going to link with that contains this function inc. Then it actually has to issue a function call. So it'll say call and kind of a placeholder for inc, right? It doesn't know the address of inc yet. The compiler doesn't know the address of inc. So it'll say call placeholder, and then later down in the object file it'll say, oh, and by the way, I left a placeholder over there. It's called a relocation entry. So please just put linker, right? Put the address of inc at this placeholder. So that's what the linker does. Linker takes a bunch of object files, just concatenates them, and replaces all of the placeholders inside all of those object files with the appropriate addresses of the symbols. That's what a linker does. All right, so what I wanted to look at was what happens with this function call. There isn't that much we can do on this side of the function call as a compiler, because we don't really know what's going on, but maybe on the other side we can do a few interesting things. So let's see. Let's make it like this instead. That's not so hot, is it? Let's see. Go like this. This is the worst part of Emacs. Okay. I have no idea how to make it not complete that. Okay, anyway. Now we have another object file, and I'll just define our function here. F, right. Oh. It's actually not Emacs, it's I mode. It's a little broken. Okay, so then we go like this. Oh. Okay, this might be worth our trouble. All right, so the thing I'm trying to explore here is how does the compiler deal with this? Right, you're given an int pointer, and then like how often does it need to read this I? That's a little unclear. So why don't we start this like this first and just see what it generates.
Shouldn't you dereference I?
Yes, absolutely. Thank you.
So shouldn't you include this file?
Nope. This is a C file. You don't include C files. I would ask the linker to do it later, but we don't actually care about this call here at the moment. I just want to see what's generated here. We know what's going to be generated here. Like, it doesn't have much choice. Okay, so ff.c here. Okay, so what is it doing? I suspect here's our loop. Oh no, not quite. That's our loop. All right, so we're adding 1 to the local variable. This is the local variable here, sitting on the stack. Whoa, sorry. Let's do it again. Okay. All right, so question is it reading this here? So it's comparing EAX being the J, presumably. Well, let's see. Wow. Which one is J? Does it get better if we do nope. -4. Oh.
-4 RBT is J, right?
Oh, I didn't do this with optimization. Then you get all sorts of weird stuff. Right, so it's actually keeping J on the stack. If it's not optimized, it keeps this J on the stack. That's really awkward. Let's see what the optimizer does about it. Huh. Oh. Nice. Right, okay, so it just stored the, okay, this should be better. Wow. Wow. So now it decided to unroll this loop. Crazy, okay. See if we can convince it.
Not passing in the optimization flag yet.
Oh, did I lose it again? Oh, there it is. Okay, anyway. It's clearly doing, so this, it's unrolled the loop a lot, right? You see the same copy of everything here. But is it reading it is the question. I wish I could tell. I thought it would be easier. Anyway, certainly, if we told it volatile, then we know it'll be reading it. Oh, in fact, nice. It decided it wasn't worth the trouble anymore. And so now it's actually loading it every time. So this must be the load here. Yeah, so it keeps incrementing this EDX until it's smaller. Okay, so this is the load of I. Okay, maybe it wasn't there, I'm not sure. Another thing you can do is you can say const. All right, so with the volatile, yeah, this is good because things could change. These values could change if you're in a multi-threaded situation, you're passing in a pointer to some data structure. Good to be able to say that for parameters as well. Yeah. Did you have a question? No. And const is the opposite. So if you know for sure that this pointer is pointing at something that no one else is changing, then it's okay for the compiler to just read this value once. And now we should have it. Yeah, we got this weird unroll. Maybe we can do a little less aggressive optimization, more readable. So, okay, looks like ECX, here it is. So it's reading I into ECX outside of the loop and then looping around it. Of course, there's another thing you could do that's even better. If you know that I isn't going to change, let's make it like this instead, right? Don't be passing pointers around unnecessarily. By value is really great, especially for for primitive types like ints and such. If you go and pass a struct, like this, now it's a little less clear, right? Passing in a pointer, we know that's a 64-bit thing that can go in a register. It's really nice. You might even want to say it's a const struct, big struct, right? Now we know the compiler can load it once. But what happens if you do this?
You put that struct on your stack.
The whole struct gets mem-copied onto the stack, exactly. Right. And that may or may not be a good idea. Depends. Right. It's probably better than going like this. Right. Okay. There was one more piece I wanted to show you, which I think was pretty cool. And it's like this. Let's see. So here we'll say until max, or index of. Let's go like this. Okay, so this function is supposed to find the index of this value inside of a buffer. There really should be a size too, but let's not worry about it. So we're looking through this buffer here to find this value. So, all right, let's try it. While, okay. And that's the max.
You need to initialize index too.
Thank you. Right, okay. So there's something really funny going on here that isn't entirely obvious at first. I'm not sure I dare look at the assembly, but let's do it anyway.
Maybe.
Hopefully it's not too crazy.
Yeah, you got to increment index.
Oh, that's a good one. Where shall we do it? And I probably should finish that. All right. Okay. Oh, it's not too bad. All right. You know, there probably should be something like this on the exam, right? A bit of assembly and what's going on question. Right? So keep that in mind. There won't be any read some assembly question. Sorry, write some assembly question. There may well be some read. Okay, so what's it up to? Let's see. Yeah, this rep, don't worry about it. That's due to a bug in the AMD K6 CPU. I was wondering, what the hell is this? Rep means repeat. Right? So what do you, like, repeat many times, return many times? But there was some bug with in one CPU, and since then GCC is always issuing this weird little function, weird little return. It's nothing to worry about. Let's see, what were we doing here? Right, okay, so there's the comparison. And it's comparing buff index. Aha, ECX. Where's ECX? Actually, it looks like it just loaded it once here. I don't know why that's... I guess it depends on how aggressive the compiler is. But in principle, at least, this... yeah, I think it depends on the aggressiveness of the optimizer here, but in principle, oh, that's why. Now I got it. Okay. Here's the problem. I'm just going to overwrite whatever's in there. Let's see if it changes the code. Okay, so where's our comparison? ECX. Here. Ah, yes. All right. Good, good, good. Whew, that was close. Okay, so what's going on here? Our loop goes from here to here. We're doing a comparison. We're comparing ECX to this stuff, right? So this thing here says RDI probably. That's the base pointer of buff. And it says that's the value of index. But we know the type of buff. It's an integer array, so it should be times 4. Because the assembly doesn't know about that. So now we have to tell it about the actual sizes. Okay, we're comparing against ECX, which is star value. But we keep reading it. So before this didn't happen, because it's safe, we didn't make it volatile, which means that this value here doesn't change, right? But now something has changed. So now it feels it needs to keep modifying, keep reloading this value pointer. What's up with that? It's single-threaded, and there's no volatile. It knows no other thread is changing it. So why does it keep loading it?
Is it because buff index could eventually hit it, possibly?
Yeah. So this is a pointer, potentially, into our buff, which is an array of integers, right? So the 11th integer in buff, that's the value. So once we get to 11, we've set it to 0. And so now we're looking for a different value. So the compiler, it doesn't know whether it is changing its own value. And that doesn't qualify this for volatile, right? Volatile means something else is changing the value. But we could still be changing the value in this case. So kind of obscure, but usually the programmer would know, right? I'm not going to be passing in, I mean, what I really should be doing in this case is like that, right? And we're good. But maybe I have good reason not to. And oftentimes, say if you're doing a mem copy, you don't have much of a choice. Right? If you're copying from between two arrays, you're going to have to pass in 2 pointers. All right, so how do we tell the compiler about this? Anyone seen the keyword? It's not const.
Is it restrict?
Excellent. Restrict. Let's just try it first. Oh, should it go before? Come on, what's it called? Is it underscore restrict?
No, it's after the star.
Really? All right, let's try that. Thank you. Okay. Good. So now we're not reading, ECX isn't being read over and over. So restrict says nothing else is pointing at this value. Right? This point, the value pointed at by this pointer is not pointed at by any other pointer that you need to worry about. So yeah, I think it means more. It probably means more generally, like don't worry about it, right? Don't worry about this value here isn't going to change, right? Even if you write to some other pointer. But in principle, I think the definition of a restrict is there exists no other pointer that points to this value, which is probably a little rough, right? In the calling function, there's another pointer to it, maybe, you know. Okay, so now the compiler knows that because buff is not a pointer to this value, you can't get to value through buff. We're okay. That can be quite important if you're moving a lot of memory around. All right. I think those were all the little compiler tricks I had to share at the moment. Let's see. Oh, no, one more. This one's pretty cool. Let's see. Yeah. All right. Oh, that should do it, right? Let's see. Double parentheses. Okay, so in this case, if we don't have this attribute const, now the compiler has no choice. Right? We have to run this function. We have to call this function a million times. Even though we're not actually using whatever the function is returning, right? We're just discarding all this stuff. But because we don't know what the function does, you know, maybe it's not safe. The function might have some interesting side effect. So we can tell the compiler about functions that don't have side effects. Maybe this f here is meant to compute the number of set bits in the value pointed in the pointer, right? Or see if this pointer is aligned, right? Is this a 64-bit aligned pointer, byte aligned pointer? That might be the purpose of the function. So here, because it's useless work, checking all these pointers and not doing anything with the value, we should be able to throw it out. Just remove all of this code. The compiler can just eliminate all of the useless work. So here, with attribute const or pure, I think both work, we're telling the compiler that this is a pure function. It doesn't have any side effects. So let's try it like that, right? So here's our for loop. Set the x to 0 and then return. And then if we remove this pure, somewhere in here is the call, right? So we're getting a ton of calls. So sometimes, you know, we don't really, I don't know, I wouldn't usually write all of these extra attributes and be really careful about all the various qualifying keywords of const and restrict and such, right? It's a lot of work deciding what's what and so on. But if you are writing a program and your profiler says, oh, you're spending a lot of time in this tight loop here, making a lot of calls to this one function, then you might want to think about, like, can I tell the compiler something more about this function? What kind of function it is, what we're doing with these, or what kind of parameters I'm passing in, and so on. That way the compiler can do a better job of optimizing. But if you do that early on, then you're probably wasting so much of your own time that it's not worth any of these optimizations. Okay, so let's play a little bit with OpenMP. OpenMP is almost like the preprocessor, the macro preprocessor in C. You know, you're saying if we do a include this. Like the first time when we're, in fact, let's actually try this before we move on, just in case you haven't seen it before. Okay, so what happens when we start compiling this program with a -e? It just runs the preprocessor first. So it replaces the standard io.h with that, and then the rest is just our code, right? It's exactly our code. So it's just a straight up string replacement. The preprocessor also does the defines, right? Same thing again. Straight string replacement, or pretty much a straight string replacement. Sometimes a macro can take a parameter, which is a little more complicated. But in any case, OpenMP is a little bit like that too. It's not really a part of the language, C, right? It's some kind of a little awkward wrapper around it. But it makes life a lot easier in many cases. It doesn't really know about types and things, or it's not really well informed about the language. It's a really powerful preprocessor, I suppose. Don't actually know what comes out in the assembly. I've never looked at the assembly that the OpenMP compiler spits out. I would imagine it's horrific. Right? There's a lot of work that goes into spinning up all these threads and setting up little control data structures for every task you need to run, and then scheduling them and so on. It's going to be unreadable, most likely. But maybe, yeah, I don't actually know how you would performance debug an OpenMP program. Maybe we'll look at that a little later, once I've figured it out. Okay, so let's do some little OpenMP programs just to get a feel for what it does. So you got to start out with just for printing. We need our omp.h, and that just provides some functions, and I don't think it provides these OpenMP pragmas that we use all over the place. Let's start with something simple. OpenMP parallel. Maybe, what's it called? Thread num, yeah. All right. So here's our first, it goes pragma OpenMP parallel. So this says that the coming block should be run in parallel on all the threads. All the threads here being a little bit loosely defined at the moment. OpenMP will pick something that seems reasonable and go with it until we change it around. So let's take a look. There it is. Okay, so all of those ran separately and in parallel. And there's an implicit barrier. So basically we run a pthread barrier here, and we run a pthread barrier there. So all of these things will, actually we can try that. Go like this. Right, so in this case, now we should get all the hello worlds first, and then only the hello agains, right? Because of this implicit barrier. I hope I remember correctly. Ah, yes. Right. This doesn't make any sense unless there's an implicit barrier. Because otherwise, every thread, it runs hello world, and it can run hello again immediately thereafter. It would just do that. There's no way we could get this ordering unless we have an implicit barrier over there. Okay, but this is maybe not exactly what we wanted. You can tell it that you want a little fewer threads. What's it called then? Num threads. There it is. Okay. So this basically probably should be how many cores you have, right? But maybe you're sharing it with another program. You don't want to use everything. That's fine. So you can tell it there, or you can tell it in your program directly. Let's not worry about that for now. Okay. So whatever goes in this OMP parallel by default runs the same code on all the different threads that you have up and running. That can get a little awkward. Right? Usually if you have a multi-threaded program, you usually want them to do different things. Right? So we can go like this if we want. Let's see, what's it called? Get thread ID, I think. Oh no, it's get thread number. Okay, good. So we can say so, all right. What did I miss? Print F, thank you. Would be better. Okay, right? So I guess in principle, we could manage it this way, and it's still a little easier than dealing with p threads, right? Now we have two threads, and they're doing different things. So of course, from there you could call whatever function you want, and so on. We could kind of spread it out that way. Sometimes we might want to just have one. Like part of the code should actually only run once. So even if it's inside of an OMP parallel, let's see. Yeah, let's do it here. We could say, or single. Let's go with single. Let's see who prints it actually. Right. So this is convenient. Sometimes you need to sort of coordinate things first with a single thread, and then you want to do a lot of things in parallel. But usually, it's not very. This isn't convenient. Generally speaking, OpenMP is mostly used for data parallel sort of programming, not task parallel. This would be task parallel. To make it data parallel, it generally speaking will be, we want to apply the same code to different data, one way or another. So we can go something like this. Let's not print. let's just have we want to sum up all the values from, now we run the risk of the compiler getting too smart for us again. But let me see. Let's try this. So we'll say, okay, let's do a sum. Okay, so far, let's actually drop this one for a moment. So far we have many threads all running the same loop. So we're going to get the number of threads times 100 million would be the sum. That's probably not what we want. Let's just try that first. And it's, oh, I forgot to print the sum. In fact, well, what do we do like this? Right, and then we had this problem with the race condition as well. Well, let's deal with both of those separately, or maybe in one fell swoop here. Let's see. Okay, so we have at least the compiler didn't get smart on us, so we got the whole code generated. That's nice. It actually generated all this summing up. So how can we make this a little better? We have a couple of problems here. First, now we're adding up. This is probably more than this value. So that is 100 million. This is 2 billion. Right? How can that be? With 4 threads. Oh, sorry, it's a sum. Yeah. So we're adding up a lot. Yeah. Okay, good. So, how long did it take to run? Long enough. All right. So to speed this up, what we really wanted to do was not to add them up 4 times altogether. We want to split the work over the 4 threads. Right? So to get a more correct program, we want to do a pragma 4. So now we're telling each thread to do a quarter of all this summing. All right, but it's still probably not a correct result. In fact, why don't we say, just to see what the correct value is. All right, that looks stable. 80, okay. This seems like an awfully small value, but that's because I think it's wrapped around a few times. Like the integer here can't hold really large values. That's okay. We don't worry about it. We want to see that value every time. So now if we drop this and we go with a 4, we get a different value. So how can we fix that? Well, these should really be operating on their own copies of this variable, right? We don't want them all writing on the same one. Well, okay, so one way we could do it, we talked about that some previous time, right? We can acquire a lock, right? We can say like this. Now the rest of this for loop is a critical section. If we do that, it's going to take forever. That's not what we want here. And we tried that a previous time, and it was terrible. So let's see if we can do something better. Really, we should have each one of these threads. It's 4 threads at the moment, but only because we specify 4. Actually, let's get rid of it, see if it changes the... all right. So see, it's still taking a long time, too. It's not great. They really should be operating on their own value. So another neat trick we can pull with OpenMP is we just say, this sum variable is private to each thread. That's really fast. But the sum is 0. It's not great. So, okay, so there's one thing we can do. We can say last private. And that means that whatever is the last iteration, last result from this for loop, that will be returned as the sum. So this was split. Like, so far, OpenMP decided to split the loop in 4 pieces, because that's kind of the default here. So it's 4 big chunks, and the last iteration of this loop running on the last thread here will be exporting its value of sum to the global scope here. Still not great. It really should be the aggregate of all of them, right? So, and this is getting a little awkward. Why don't we go with a proper sum? Hopefully it doesn't wrap around that. Okay, it's better. Right. I think a better solution, and this is probably the fanciest and weirdest thing in OpenMP. You can tell it that to do this combining on its own, it's called reduce or reduction. Which one is it? Reduction. Because it's so common. You may have heard of this paradigm called map reduce. That's something used for distributed computing. But it's really common in any case with parallelism, like you want to work separately and then combine your results. The map is the separate work, and the reduce is just put them all together. In OpenMP, it's called reduction. So we're actually saying, here we say, oh, make sum a private variable inside of this loop. But then before you exit, take the sum. Here, this is the operation, right? Take the sum of all of the local private sum variables and make that available out here. See how big the sum is. Okay, that looks like a proper sum. I think that's the right value. Usually they end up looking something like that. Okay, it actually ran pretty fast too. Let's try it with, this is not single thread, this is 64 threads now. But let's try it with, what was it? Thread, num threads. But compare this to working with p-threads, right? Like, there's just a lot of overhead in trying to set this up. What do we need? In order to run this with p-threads, I think we'd have to set up in this outer loop, we'd have to say, oh, make a little struct that says where each thread should start, index start to index end, right? And then call this pthread create for all of them, and then a return value and add them up, and it's easily going to be 30 lines of code just to manage the initialization of this thing. So quite helpful. Okay, before I move on to more fancy tricks with OpenMP, tell me what you're not getting. Is it all really obvious?
Until you try it later.
Yeah, exactly. Right. I do recommend that you try it later. I think the point of this lecture is more to show you kind of what's there. And of course, we'll do a homework with it, so you get to play with it. But there's quite a bit there. So let's take a look at a few other things.
What was the one value that we got? That was like 887 million when we did it single threaded.
Oh, right, but that's before I changed the type here. Right. But we can do it in single. In fact, I'll go like this. It'll be the same value. Okay, so single-threaded, 30 of a second, with not a whole lot of code. In fact, I think we can drop this one if we want. We can put it here. In this case, we get to put it here. I think that's it. Aha, this was num threads 1. This is a little weird. Look, it's faster. Hard to tell why. Okay, so let's just tell it to use however many threads it wants. And there it is. Okay. Of course, this is a pretty beefy machine. But in any case, it's nice where you can kind of get a quick speed up. And the only reason we got the speed up was this reduction here, right? Because otherwise, we don't even get a correct result. And it runs slow. Right. Okay, so let's see what else we can do here. We'll resort to some prints again. Oh. Get thread num. Okay, so I want to just print out, so we get a feel for what, which thread is running when. Oh, I deleted the 4, right? It was just parallel, which means run all of this in parallel on all your cores. Let's do like that instead. Yeah, I like it better that way. Okay. So we can actually tell it how it should be splitting this work. So we could say schedule static 1, and now it's going to split the work in 1,000 pieces, right? Chunks of size 1. And all of our threads will kind of divide it between themselves. See what it does then. Oh yeah, it's like that. I'll try to clean it up a little bit. This is getting a little out of hand. All right. Interesting. I'll try this with here, 2 threads. Oh yeah, okay. So I'm sorry about the print order. Actually, we can fix that. There. So in printing, they'll just come out in any order. But you see, thread 0 got 996, thread 1 got 997, so on. So this got split up that way. So we can change the schedule. We'll tell it you can get 4 at a time. Right, so now we have 4. Okay, so this seems convenient. It's not really clear when you would need these schedules.
Yeah. So the threads aren't literally alternating 1, 2, 3, 4. They've just had the numbers divided up between them, and then they run whenever they run.
Yeah. So the work is divided that way, but they're not told in which order they have to execute. You can, of course, tell them if you put a barrier in there, then they would be running in that order. Yeah, let's do that. Now we can ignore the schedule, I think, and we should get a nice. Oh, is it just pragma barrier maybe? Let's see. Oh, maybe we do need the schedule. Otherwise, it's not split up properly. Yeah. Okay. There it is. Right, but we don't want that.
What does it look like if we run without a sort?
Oh, sorry. I had a sort there. Ha. Good. Yeah.
One is getting all the odd numbers.
No, it doesn't. That doesn't look anything like what I had hoped for. That can't be the right barrier. Let me see. So this is a problem in general with OpenMP. You know, all these pragmas. A pragma, by definition, I think, it doesn't do anything if it's not defined. So you can say pragma foobar and hope that it does something for you, but it will silently just not do anything. So I think when I said pragma barrier, it just didn't do anything. Let's see. The barrier. Pragma omp barrier. So what's it upset about? Oh, it doesn't like that. May not be nested inside of a work sharing region. Well, I guess that makes sense. This will just slow things down. Okay, if we wanted it to come out the right way, let's not worry about it right now. You know, if you actually want them to come out in sequence, probably you shouldn't be running it multi-threaded anyway. But okay, I have one idea. I think it's called, or sequence is what it's called, I think. Wrote this down somewhere. Ordered is what it's called. Let's see what happens then. Must be. Oh, okay. Like this. Okay, so there it is. So this seems awfully strict, but let's see what it does when we split it like that. Yeah, okay. So now it's coming out. So you got what you wanted, but yeah, it wasn't great. I think what happens here is the for loop has an implicit barrier either at every iteration, like every chunk, or perhaps that implicit barrier is this one here, the unordered. Okay, but so I don't know if this, yeah.
No, so what would happen if you had something more like complicated for instead of incrementing I, you did something like maybe more fancy?
Shall we do a? You're not interested in the ordered, right? You're interested in just generally, yeah.
Like, if there wouldn't be a way for it to divide it up, like if I was like set equal to a value of some function.
Oh, I see. So I think that I mean, it has to be a for loop. So, and I don't think you can have an arbitrary function in here. I could be wrong. But we can do something about the the scheduling. So maybe somewhat related, but not quite. Like, okay, the loop probably has to be this way, a simple one. Otherwise, OpenMP won't know how to expand it out. But here we are going with a very simple static schedule, and that can be really inefficient. Say we were to go sleep I. This is probably too long. We don't have that many minutes left. 100 seconds. Okay, that would work. Nice. This gets inconvenient, right? Because now the last thread is going to sleep 1,000 seconds times 10. Well, okay. Well, 1,000 seconds total. And that's 20 minutes. So 15 minutes-ish. So we can't do that. So it won't finish on time. But really, if we have, actually, let's try it. Just see how long it takes. That's okay. If we have many threads, yeah, it's still taking long because the last thread, we're waiting for the last thread, basically. But what if they split it some other way, right? In fact, if we go like this, then I think it will finish on time. Well, we have very little time, but basically now they're splitting. They're all working on the long work at the end, right? All 64 of them. It's not like the first thread gets all the easy work and the last thread gets all the hard work. Now they're all splitting it. This wasn't a really great example. But anyway, I think I'll just sum up with this, that a static order like this with a chunk of 1 is inefficient in terms of overhead. Like, here you have a lot of, for every little chunk, you have to do some coordination. It's really not great. But then if you have a large static chunk, now it's inefficient because you might have unbalanced work. Some threads finish and have nothing left to do. At least if we have a very large chunk, then maybe that's what I should have done. You might have some threads that have a lot of work left to do and some other threads doing nothing. An alternative that you can do is to say dynamic. With a dynamic schedule, OpenMP will decide, so first all the threads get to do 10. Right? But then whoever is finished get to do the next 10. As opposed to splitting everything up evenly, every so many pieces, chunks around the loop. With dynamic, it's just sort of a queue of these 10-sized chunks. So every thread comes in. Well, I underestimated how long it would take to finish all that sleeping. With dynamic, you have a first in, first out queue sort of thing where all of the threads sort of take work as they become ready. And then finally, there's another one that's called, maybe we'll play with that next time, it's called guided. And here, it'll start out with large chunks, and then slowly grow the chunk size so it's smaller and smaller toward the end. The point of this being that in the beginning, if you have a large loop that you all need to work on, everyone can take a large chunk and it's no problem, right? Because there will be more work for the others. So balance isn't important in the beginning. But toward the end of the loop, you're kind of running out of work. You can't assign a chunk of 100 to one thread and then leave the other ones idle. Toward the end of the loop, it should really be a much smaller chunk size, and that's what this guided does. I think we need to have a more, we need to have a good example to see this behavior in practice. Okay, so we'll talk some more about OpenMP next time, and then also a little review of the topics for the final, for the midterm. I've updated this book thing a little bit. There's just a bunch of extra references. Find some really good materials out there. I'm not going to copy paste that. I suggest you take a look at that. And I'll post some more things on Piazza as well. All right, see you later.